This is the Mathematics Education Podcast from mathedpodcast.com.
Welcome to the Math Ed Podcast. My name is Ashley Black from the Infinite Tangents Podcast at tangentspodcast.com. Today I'm joined by Sam Otten, an assistant professor in the Department of Learning, Teaching, and Curriculum at the University of Missouri. We're going to be talking about his article from Mathematical Thinking and Learning, Volume 16, titled The Mathematical Nature of Reasoning and Proving Opportunities in Geometry Textbooks. Thank you for joining me, Sam.
Thank you. I'm curious what it's going to be like on this side of things.
So let's start where you like to start, which is, can you tell me a little bit about the topic of your dissertation?
Sure. I did my graduate studies at Michigan State University, and my dissertation focused on middle school mathematics classrooms. And I looked at a variety of classrooms from different states, all teaching some early algebra content. And I looked at the student discourse, and particularly I looked at the ways in which the students participated in the mathematical discourse. And I analyzed how much of the mathematical ideas and the mathematical relationships that were expressed in the talk were actually contributed by the students rather than by the textbook or the teacher. And that was guided by Beth Herbel-Eisenman from Michigan State, who I worked with for almost my entire time there.
Nice. So what motivated you to conduct this study of geometry textbooks?
My interest is in student discourse, but particularly in students' engagement in the mathematical practices. So if you think in terms of Common Core, it'd be like practice 3, constructing arguments and critiquing reasoning, or the problem solving, or looking for and using structure. I'm really interested in how students participate in those kind of mathematical activities. And one that I think is probably the most important is reasoning and proving. I think that's just really central to what it means to do mathematics. I think that's what makes mathematics fun and rich and beautiful. I also think reasoning and proving is what makes mathematics useful in life. I use careful reasoning and thinking about logic and arguments and assumptions. I use that in my life all the time. To be honest, I don't really use factoring polynomials or rational expressions very much in my life.
You're not using the quadratic formula every day? You're breaking your high school math teacher's hearts.
I think every day when I wake up, it is one of the first things that crosses my mind. But so I did have this interest already in reasoning and proving, but what brought me to the geometry textbooks was I kind of was hearing different people talking about students proving. Sharon Sank, in her 1985 piece, she talked about how the students across the country were not very good at what she called textbook theorems. Students were okay at proving the sort of student proofs, but then Sharon Sank said they were really poor at proving what she called textbook theorems. And so I was kind of like, what's the difference kind of between students' proofs, or what students are supposed to prove, and then these textbook theorems. And I also was going to some teacher conferences where I was hearing some teachers talking about how to teach proof. And they said, they were getting frustrated because so many textbooks would have what they called contrived proofs, or I even had saw one teacher who said stupid proofs, and that's what she called them. She's like, these are stupid proofs, here are good proofs.
I've definitely been in some of those conversations.
Yeah, I mean, you probably will recognize some, or you could give some examples. The one that I remember she gave was a line segment that is broken up into parts, and so you have overlapping line segments, and then you have to prove that the little piece on the left side is congruent to the little piece on the right side, and you subtract out the overlapping part in the middle. So, I mean, I agree, that's a very stupid thing to prove, and it leads to a stupid proof. I mean, I think the idea behind them is to give students a chance to practice the process of, starting at where you start and move through, make sure you justify each step, and end where you're supposed to end. Mm-hmm. But I think there's kind of a disservice when you give students a chance to practice that with really silly, boring, stupid is probably a good word, stupid things. So I was kind of hearing this conversation, but what I wanted to do is I wanted to get a better sense of what was really going on, and I wanted to see if I could analytically identify this issue when I looked at textbooks. Like, can we actually scientifically distinguish between the stupid proofs and other proof opportunities? So I had this kind of idea. I was intrigued. I wanted to really dig into some geometry textbooks and see what was going on with the proof opportunities. Michigan State was really great because they gave me an opportunity to kind of build this study up, and I couldn't have done it without some of the supports that Michigan State had. So first of all, I had a class where I wrote a paper, and I decided to write my paper where I reviewed existing literature on basically analyzing the proof opportunities in textbooks. And then I had a comprehensive exam paper. I basically built on that literature review, and I wrote an argument for why we need a new study. Like, here's the existing studies, but we need a new study. And I argued that the new study needs to look in geometry textbooks where there are really the most reason improving opportunities, because prior to that, the textbook studies had actually been everything outside of geometry. There were middle school studies, there was an elementary study, there were algebra studies, there were advanced algebra pre-calculus studies of the proof opportunities in the textbooks. And those researchers had a good point. They said, we know there's lots of reason improving in geometry, so let's see what reason improving there is outside of geometry. And I think that's a valid point, and I'm glad that they did their studies. But I made the case that we also need to look at geometry textbooks, because that's where the most reason improving opportunities happen. And I had this sense that there was some issues going on there. It wasn't like it was all perfect in geometry, and we just need to have more of it happening in algebra and pre-calculus. I think that we could still understand better the reason improving opportunities in geometry. So with my comps paper, I made the case for that study. And then I was looking at this comps paper, I'm like, wow, I made the case for this study. Can I actually just go ahead and do the study? So I applied for some funding from the Michigan State College of Natural Science, and they gave me like a summer grant to actually do the study. And I got together with some friends, because I couldn't really do it by myself and definitely needed some help. So some other graduate students at the time helped me, and they were the co-authors on the article. That's Nick Gilbertson, Lorraine Males, and Dan Clark. Lorraine Males, by the way, is now at the University of Nebraska, but she was at Michigan State with me at the same time. So then we got funding to actually do the study, and then, as if that wasn't already enough, the next semester Michigan State actually offered a Reasoning and Improving class with Kristen Bieda, and in that class, Kristen basically supported every student in doing some writing about reasoning and improving. So for me and my colleagues, we were able to actually use that class to write the first version of this manuscript. We had to do quite a bit more work later with reviews and everything, but that's kind of where it all came from and where the motivation was.
Nice. So which textbooks did you end up looking at, and how did you conduct your analysis of them?
We looked at 6 textbooks. We were looking only at standalone geometry courses, and we wanted to get a pretty broad range of the books that are used in the United States so that it covers most of the students. So we had Glencoe, Geometry, Holt, Prentice Hall. So those are 3 that people usually would think of as publisher-developed geometry textbooks. We also did the UCSMP Geometry, which is a university-based project. And then we did 2 other geometry books, the CME project, which is the one that has the habits of mind as one of their kind of guiding design principles. And we also did a book published by Key Curriculum, which is called Discovering Geometry, and that one's the one written by Michael Serra. Michael Serra, the curriculum developer, not from Arrested Development. So those were the 6 books. To analyze it, we really built on previous studies. We didn't want to reinvent the wheel. So we looked at Stylianides' 2009 piece, which was also in Mathematical Thinking and Learning. And from him, we really took the broad scope of reasoning and improving activities. It's not just proof. Reasoning and improving involves identifying patterns, making conjectures, maybe some initial empirical justifications of that pattern or that conjecture, and then eventually, leading to proof. But all of that stuff is under this umbrella of reasoning and improving. So we kind of got the broad framework from him. And then Thompson, Senk, and Johnson had a 2012 piece in JRME. We actually got advanced copies of that work because Sharon Senk was at Michigan State and we were talking to her about this. From them, we actually took specific codes for the type of justification that might appear in a textbook. Like, does the textbook give a full deductive proof, or does the textbook just give some confirming examples, or does the textbook leave the justification for the student, like if the textbook says, you will prove this in number 12, that kind of thing, or does the textbook actually omit the justification? We got all that from Thompson, Senk, and Johnson. We also got from them some codes for things that the students are asked to do. Like, is the student asked to prove a statement or, give an argument for a statement? Is the student asked to make a conjecture? Is the student asked to find a counterexample? Those kinds of actions that are asked of the student. So that was our basis. But then we did some piloting And we ended up modifying the framework to fit geometry textbooks, so we had to add some more codes because geometry books did have a lot more reason improving. The other big things that we did, trying to get at this issue of the stupid proofs, or this issue of the contrived proofs, we actually added a whole new dimension to the framework, and we called it mathematical statement or situation. So if you imagine a reason improving opportunity, you're looking at a book, you maybe see like number 12. And you're like, oh, this number 12 involves reason improving. Or maybe you're looking at the narrative or the exposition section of a book, and you say, oh, look at this book just presented a theorem with a justification. So that's an opportunity for the students to think about reason improving because they're seeing a theorem and its justification. If you can put your finger on one of those opportunities, for us, we said, well, we want to actually code for this dimension of what's the nature of the mathematics that's being reason improved around. And for us, the big distinction was, is it a general claim or is it what we call a particular claim? So if you're looking at number 12, is it asking the student to prove or justify a claim about all isosceles triangles? They have to somehow establish the truth for that entire infinite class of mathematical objects. To us, we coded that differently than looking at number 12, and it has a picture of one particular isosceles triangle, and it's saying, prove something about angle A in this triangle that we've drawn for you. And that's where we felt like we were getting pretty close to what the people were talking about with contrived proofs versus more authentic, real, interesting, kind of more, what I would say, more mathematical proofs. Because for me, the point of proofs is to establish some kind of general truth. So if you're not even starting with a general claim, then to me it has a different flavor. The whole activity has kind of a different flavor. Another thing I wanted to mention is that through the analysis we found that it's not completely clear-cut between the general opportunities and the particular opportunities. We actually ended up with a code called general with particular instantiation provided. And what that was if you think about just a proof opportunity, for example, there might be a proof opportunity where the student is asked to prove a general claim. So just to use the isosceles triangle again, prove something about something is true for all isosceles triangles. So that's general. But then sometimes the textbook right underneath that claim or right with the claim would actually give a specific diagram and have it labeled and maybe connect that to the claim. Like really what you're proving is angle A is congruent to angle B. So we still coded this as general, but we have it as general with particular instantiation provided because within the opportunity, students could think about it generally, and they could prove thinking about the general claim itself because there is the general claim there. Or a student could take this as an opportunity to prove something particular because they might just work with that given diagram already labeled for them, and they might just say, oh, I'm going to prove something about that diagram. In the latter case, to us, it was very similar to having a particular proof opportunity. But it's not the same, so we coded it differently because it does have the general claim kind of hovering above everything. And so that was what we used there. And we think this is important because, like Dan Chazen has found, sometimes when students prove something and there's a diagram that they used in the proof, sometimes students think they only proved it for that one diagram. They don't realize that they've actually proven it in general. And so this is an important step to realize you can establish something for a diagram, but if it's sufficiently general, if it's used as kind of a generic example, then you've maybe actually proven something for an entire class of objects. So that bridge or that transition we think is important, and so we tried to capture that with this separate code. So there's then general, particular, and then there's this general with particular instantiation provided. So we added that dimension where we wanted to code general and particular of the mathematics being proven. We kept that very separate from the kind of justification that's given. So previous analyses, they would code like, okay, the student is asked to prove, so they would code that as like a proof opportunity. And then they would also code like whether it was supposed to be a deductive argument or an empirical argument. And people might think that that's kind of the same thing. Like, oh, if it's a general claim, then that would be coded the same as having a deductive argument. Or if it was a particular claim, then maybe that's going to have an empirical justification. But for us, we wanted to keep those very separate because we said if you have a general claim, you can justify that with deductive argument, or you could justify it with empirical evidence, or you could justify it some other way. And then if you have a particular claim, you could prove a particular claim with a nice 2-column proof argument or something. Or you could justify a particular claim by slapping down your ruler and measuring something and saying, oh, I measured it, that convinces me that this is the same, or something is true about the diagram because I measured it, or because I did some kind of empirical example. So for us, we said these are really independent. Although we might ideally hope that a general claim is justified with deduction, because you kind of have to do it that way, although we'd hope that there's that connection, we think they're actually separate, especially when you're coding opportunities in a textbook. We wanted to just code the nature of the mathematical statement, separate from whether the student is explicitly asked to do it deductively or do it some other way. So that we added that category. We also had in our analytic framework, we had a category, opportunities that were about reasoning and improving. So instead of like doing reasoning and improving, it was a question about, what are the strengths of a 2-column proof? Or what are the strengths and weaknesses of a flowchart proof? Or it would be something like, how can you use axioms in a proof? Or how are axioms different than theorems? Like questions that were actually stepping out and asking the students about the reasoning and improving process. We had a separate kind of category of codes for those.
Thinking about how you're thinking.
Yeah, it's really kind of, you might do reasoning and proof all day, but it's also good to have those opportunities to step out and think about what you've been doing. It's like, oh, wow, I did use axioms in that way. Or, oh, flowcharts do have this advantage. It allows me to see something that's maybe harder to see. So stepping out and having those opportunities, it seems like that's important to have in the mix as well.
Yeah, agreed. So I'm here today talking with Sam Otten about the article, The Mathematical Nature of Reasoning and Proving Opportunities in Geometry Textbooks. So as you were looking through and conducting the study, what reasoning and proving opportunities did you find in the exposition section of the textbooks?
In the exposition, so this is kind of the written narrative part where the textbook authors are kind of speaking to the students as readers, we did find more reasoning and proving opportunities than have been found in other books. And this was true overall, as you would expect. The geometry books have more reasoning and proving in them than people found in middle school textbooks, or than like Thompson, Senk, and Johnson found in Algebra, Algebra 2, Pre-Calculus. Geometry also had more than John Davis, who studied the Core Plus textbooks, the integrated textbooks. So geometry really does have, as we all kind of know, it does have the most reason improving opportunities. In the exposition, we found about 2.5 to 5.5 reason improve items per lesson. And when I say per lesson, I should say this is a random sample of lessons. We didn't actually look at every single lesson. We randomly sampled lessons from each chapter of each book to get a representative sample. So we feel we can make claims about the books overall. So in the exposition, 2.5 to 5.5 reason improving opportunities per lesson. Those would usually be theorems, kind of, here's a box and it has theorem 4.2 in it. That was very common. Or sometimes it would be a worked example where the textbook would say, here's a proof problem, but we've also written for you the solution to it. And so because it was completely presented, we consider that exposition, and that would go into this count as well. In terms of what we saw for the kinds of justifications that were given, it was actually fairly evenly spread. There were deductive justifications given, there were empirical justifications given, there were times when it was left to the student to justify it later in the exercises. There was also a pretty big chunk of time where there was no justification given, which confirms what Thompson, Senk, and Johnson found in like the algebra and pre-calculus books. They say, wow, it's actually pretty common to have a claim with no justification given. And if you want to see particular percentages by book in the article, we report that all in tables. But what I want to comment on here is that issue of the general and the particular. And in the exposition, things were overwhelmingly general. So the exposition, it had general claims about all isosceles triangles, it had general claims about all parallelograms, it had, general claims about all kinds of general things. And this was across all the books. All the books were very general in the kinds of opportunities that they had in their exposition. So when the textbook authors are writing for the students, they're doing lots of general things.
I'd find that just a really interesting conclusion that there's so much general stuff in the exposition, because when I think about the geometry textbooks I've been through, it does tend to be the general followed by having kids do really, really specific things.
Yeah, there was a lot of general things like you're saying, and actually the times when we did see particular, statements or particular opportunities in the exposition, they were almost always worked examples. So the only time you would really see something particular was when the textbook author was kind of playing the role of a student. Like, oh, here's something that you might do as a student, but I, as the textbook author, am already going to include the worked solution. So those were really the only times that we saw particular opportunities in the exposition.
So what were you finding when you were looking specifically at the student exercises?
So the student exercises, what we found really kind of confirmed and gives some specific data to those claims and those conversations that I was hearing that led to this study. We really did find a lot of particular reasoning improving opportunities. The majority of the time. I mean, in the exposition, it was a vast majority of the time that things were general. In the exercises, it was a majority of the time that things were particular. So it was basically a complete reversal. And so if so examples of this would be, a problem where there's some parallel lines and maybe there's a transversal on there and it says, prove that angle 1 is congruent to angle 5. But it's not framed as any kind of general proof about parallel lines in general or transversals in general. It's just posed as, you are proving something about this one diagram that has been written on this page. So once you've proved it, you've established the truth of something about that one figure, that particular diagram. Mm-hmm. And so you can imagine lots of these, and that's what we saw. We saw lots of these. And in fact, the majority of the reasoning improving opportunities were students proving or doing some other kind of reasoning improving activity, like maybe they were finding a counterexample, maybe they were conjecturing. But the proving ones are a subset of this, a lot of particular situations. I should back up too and just say, to give you a sense, we found about, depending on the book, there was between 7 to kind of 15 reasoning improving exercises per lesson. Now the books varied in how many exercises they had total. I mean, some books would have like 40 or 50 exercises per lesson.
Yes, they do.
And so maybe and they might have 15 of those on average be reasoning improving. Other books might only have 15 or 20 exercises, and in those cases they maybe have 7 of them as reasoning improving opportunities. So the percentage-wise, Prentice Hall, Glencoe, Holt, they had like 20 to 24% of their exercises were reasoning improving. So you can think to yourself, about a quarter or a fifth of the time in the publisher-generated textbooks, the students are doing reasoning improving. That still leaves, maybe 75% of the time that they're doing things in geometry that are not reasoning improving. But then in other books like CME, it was about 40% of the time, so 2 out of 5, that the exercise involved reasoning improving. But again, that still leaves 60% of the time that they're doing geometry not under the umbrella of reasoning improving. But to go back to that point about the particular, we saw lots of particular. That was kind of our main finding, and we wanted to give some analysis to back up this claim about what are the things that students are proving. What students are proving is really qualitatively different than what they are reading or what they're seeing from the textbook authors. And what I would say is that what the students are proving, or what they're doing their reasoning and proving around, is qualitatively different than what the mathematics discipline really thinks of with regard to reasoning and proving. I mean, I think the mathematics discipline really views reasoning and proving as, making general conjectures or finding general truth and then establishing that truth for all possible cases. And that's, that's why we have proof. That's what it serves. It also has a good explanatory function, but at its heart, it's establishing these general truths that become mathematical knowledge for the field. And the students, in large numbers, are not really having a chance to experience that. They're experiencing these kind of contrived, I have to prove something about this one particular diagram. I would say maybe that doesn't feel as important or as rich, because who really cares about this diagram that the textbook authors just wrote for me to prove something about? It's like they constructed it so that I could prove something about it, and now I have to prove something about it, and what's kind of the point of it? They're not really feeling that power of, wow, I discovered something, and now I actually know why it's true, and I can actually prove to you that it's true. So to me, it does have that different feel to it.
Yeah. So is there anything you worry people might take away from this article that you didn't intend them to?
Yeah, I mean, I think I should put a couple disclaimers. So, like, just now, I was talking about this, what the students might experience or what the students might feel. And we do have research on students I'm thinking of some Chazen work where students did not really understand what they were proving, or they didn't realize that they needed to do deductive proofs. Or we have other work where students don't quite understand the whole reasoning and proving enterprise. They feel like it's kind of forced on them and arbitrary. But all of this that I'm saying, and that in the article in our discussion, we do some of our own conjecturing about how what we're seeing in the textbooks might relate to students. But I want to make sure everybody takes that with a grain of salt, because we did not actually study any students. We didn't look at students interacting with these books. We didn't look at the student work as they're solving these problems or these exercises. So really, any of the things that we say or write about how students might be experiencing these opportunities or what students might learn from it, that's all just conjecture. The things that we're on a firm ground to talk about are the opportunities that we saw in the textbooks. The other thing that I would probably say as a disclaimer is we did not set out to pit books against each other or to have like a horse race between these 6 books and see which one's the best and which one's the worst. I've talked a little bit about the publisher-developed books versus like the project-based books like CME or UCSMP or Key Curriculum. But we didn't actually write about them that way. We just wrote about the 6 books as the 6 books. We didn't categorize them, or we didn't say traditional versus reform or anything like that. And we tried not to really say anything about what would be better or worse. I think it would be a misappropriation of this study if somebody tried to say, oh, Sam Otten and Gilbertson, Males, and Clark, they said that CME is the best, or they said that Prentice Hall is the best. Or we really don't say anything like that, and we don't want anybody to take anything like that. We just want to report on what opportunities we saw and the percentages of the opportunities. If you're interested in the particular kind of activity, like conjecturing versus finding a counterexample versus fill-in-the-blank proofs versus full proofs, if you're interested in that breakdown of those kinds of activities, I'd refer you to Table 8 in the paper. It does have that breakdown, and that's what we tried to do. We tried to really break down percentages and the sort of frequencies of these different reasoning and proving opportunities, and we try to bring up this point, which is kind of the new contribution, about general opportunities versus particular opportunities and how that's separate from deductive justifications and empirical justifications. But we don't declare a winner. We don't say what's best. We don't know what's best. Like, I don't know if 24% reasoning and proving is the right percentage to have. Maybe it's 40%, maybe it's 30%. The right answer is probably that it depends on the students, it depends on the context. So teachers might know what they want to aim for, and then they could look at their books. So I think districts, teachers could use this to compare the books, but we definitely can't say which one's the best, or we can't make those value judgments.
Yeah, one of the things I was thinking of is I've sat on some textbook adoption committees, and just the breakdown of the different types of problems and thinking about, well, this is how I like to teach it and how my department likes to go at these subjects, and having that breakdown would have been useful in choosing textbooks.
Yeah, I mean, I think districts and teachers, they can actually make some value judgments that I can't make as a researcher. Like a teacher might say, I, as a geometry teacher, I want to have my students doing a lot of conjecturing, or I want them to have some general proving opportunities instead of just all particular proving opportunities. Now, a teacher can have that value, and then they could use this to maybe inform a decision about what book they want to use or how they might want to draw on their textbook. Or maybe they just already have a textbook and they just want to know, do I maybe need to modify my textbook a bit to meet my own values for reasoning and proving teaching?
So now that you've completed the study, in what ways are you thinking of moving forward with this information?
3 things I was going to mention about moving forward. One is that we actually did some additional analysis, and it's going to be published very soon in the International Journal of Educational Research, actually in a special issue of Reasoning and Proving. So if the listeners are interested in Reasoning and Proving, you probably want to keep your eye out later this year for the International Journal of Educational Research. But we have a piece in there where we look specifically at the chapter that introduces proof, where we were just kind of curious, do the books differ in how they start off the proof game? Nick Gilbertson, one of the co-authors, he actually, with support from Michigan State, is doing a follow-up study where he's looking at the teacher's guides and analyzing the kind of supports that are in the teacher's guides, and is seeing if there's any additional insights that are given. Because we looked specifically at the students' editions, at kind of what opportunities are given straight to the student, but he's looking at the teacher's guides as well. He's presenting at NCTM in New Orleans on that, so he's got some preliminary results, but he's still working on that. And then one thing that I'm hoping to do, I'm collecting some classroom data this year, including geometry classroom, and I'm hoping to actually look at some students. So like I mentioned how we didn't look at students, I think a good next step would actually be to take these distinctions that we made in our analysis and actually follow them into the classroom. How do teachers enact them, and then how do the students actually respond to them and perform on them? And maybe even just students' attitudes towards reasoning and proving. Does there seem to be a connection or a relationship there? I also, I've done some work with Michelle Cirillo at the University of Delaware. Both of us are really interested in reasoning and proving, but so far our collaborations haven't actually been on reasoning and proving yet, but we have this kind of hope to eventually be able to do something collaboratively where we do some further digging on reasoning and proving. So hopefully I get a chance to actually do that work with her as well.
Excellent. And so for the last question, just to keep the status quo, what would you be doing if you weren't in mathematics education as a career?
Yeah, I've asked this question of so many people, so now I get to kind of talk about myself. So from middle school all the way through like my first couple years of graduate school, I actually composed a lot of music. I've played piano since I was about 3.5 years old, and I've played guitar since I was probably 12 years old or so. And I've kept playing both of those. And I really love composing music. I like performing music and accompanying people or playing at weddings, but what I really love is creating my own music. And lately I haven't really had a lot of time to do that. Basically once I got to the dissertation stage, and then I started having kids, and now, working on faculty at the University of Missouri, I don't have as much time for composition, but if I wasn't in math education, I would definitely be doing more composing, and I might even be still trying to kind of make some money at it, like do some performances around the area, probably do more weddings and dinner parties and things like that, and then trying to kind of get my own music out there. So I think that's what I'd be doing.
Awesome. I wonder, I fall on the art side as well if I wasn't in teaching. I'm curious how much like the art music blends over. I'm going to have to start taking some unofficial surveys. Yeah,
I know. A lot of people, too, that have heard me play piano or they know of my music, they'll be really surprised when I say I'm in mathematics or, mathematics education. But I really see a lot of connections between math and music.
Oh, yeah.
And I do some kind of mathematical analyses of my music. It's not like atonal, really weird-sounding stuff, but I'll try to find ways to kind of put some symmetries in there in different ways rather than just kind of ABA, that kind of basic symmetry. I try to think of lots of different ways that I can have symmetry, and sometimes it's just for my own intellectual pleasure, but it's really fun. And I think there is the structure in music and the structure in mathematics, and kind of putting your brain and thinking about that structure can be beautiful in both situations.
I completely agree with you there. So this has been the Math Ed Podcast, talking with Sam Otten about his article, The Mathematical Nature of Reasoning and Proving Opportunities in Geometry Textbooks. My name is Ashley Black from TangentsPodcast.com, and I want to thank you, Sam, for allowing me to come on and do a bit of guest hosting for you. This has been really delightful.
Oh, thanks so much for doing it, and I enjoy your podcast too. Last year it was a lot of fun seeing some of the stuff that you've had. It's very kind of teacher-oriented. I don't know, how would you describe it? To me it's kind of teacher-oriented, but pretty fun and clever and creative too.
Yeah, I mean, you're going at the research side of things, which is great, and I'm sort of the other side of the coin of taking a look at teacher stories and what teachers are doing directly in the classroom.
Yeah, and I know you have some new stuff in the works, so I'm definitely going to be looking for the new things being posted there.
Yeah, season 2, I guess it would be, is going to be starting up again soon, kicking off with some interviews I did from the Park City Mathematics Institute this past summer.